almost time. It's almost time. Let's chill out for a bit and then we'll start in a bit. We'll start on the top of whenever we say we'll start, because we have to wait for the thing for the LinkedIn post to go live as well. So we have 3 minutes to kill. So yeah, we're gonna be working on, what is it we're gonna be working on? We're gonna be working on trying to do mailboxes, learning how mailboxes work, basically. And then the other thing we're gonna work on with mailboxes is we're going to try and see if we can get this NRF54L15 SoC. It's got two CPUs on it. There's the main application processor, which is the ARM Core M33, and then it's also got core processor, which is the VPR CPU from NRF, and we're gonna try and get those two speaking. Spoiler alert, I don't know if anyone's here already, but I'm gonna say it already. Spoiler alert, they're not speaking at the moment, and we might have to deal with some bugs, which is pretty good for our broadcast. Yeah. So we might have to deal with some bugs and fix up some stuff and see how that goes. Other than that, it's gonna be cool. So yeah, it's another minute, and then we'll do an introduction, and we'll get this going. Yeah, get this going in a minute. Let me know if you're online, and let me know where you're watching. Let me know if you're online and if you're around, and I can let me know where you're watching from, and that's cool. So, and then we can start in around a minute. When the LinkedIn post goes live, we can go live as well. So, just giving everyone a chance to get in on time and be there, I think. Yeah. Hi everyone. I think welcome. Hi everyone. My name is Zach, and I'm an open source developer. And I'm at the current time, I'm working a lot on Zephyr applications. And basically I do these live streams as many times in the week as I can to see if I can learn stuff and discover stuff, and also kind of basically contribute to the community. And yeah, so the way this works is I usually go through some sort of challenge or code that I'm going through, and it's a free flow thing. I'd welcome you to ask any questions that you have. I'd welcome you to do any suggestions that you have. Do let me know if you can hear me or not hear me, and that'll be amazing. Yeah, so let's think about this. So what are we going to do today? As you can see from the title, today we're going to explore the Mailbox API in Zephyr. And basically this, I think it gives us an opportunity to kind of jump around and go like Zephyr IPC. So Zephyr has interprocessor communication, and what we're going to try and do is we're going to try and get two processors to communicate. And today's choice of processors communicating is going to be the main ARM Core M33 on the NRF54, and then see if we can get that to talk with the soft core RISCV-VPR CPU or co-processor as they name it. So let's discover a few things before we get into this code, and let's see what we can kind of surmise and know how it works, and then we'll kind of start looking at mailboxes, and then I think at the end we'll see if we can run a couple of samples and see how they work if possible. Okay, cool. So an overview of what interprocessor communication. The IPC service API provides an interface to exchange data between two domains or two CPUs or CPUs. So, and I think domains is stuff like if you have buses, if you have like an AHP bus and a PB bus, and there's a way of those two communicating. And I think that's what domain stands for. Yeah. But what we're going to try today is to try and to get two CPUs to speak to each other, and so that's going to be a lot simpler, or maybe a lot more complex. An IPC service communication channel consists of one instance and one or several endpoints associated with the instance. Aha, I see. So there's one channel, and then there's a number of it's almost like a Discord or a Alexa or a Erlang channel, if that makes any sense to you, or a socket where there's one socket and everyone can plug in, and a lot of people can plug in into this socket, and they can see and they can send in data and pull out data and such. And an instance is the external representation of physical communication between two domains or CPUs. The actual implementation and internal representation of the instance is peculiar to each backend. So this is sort of like almost DMA-like, because DMA works differently for different people. So we have naming terms here, nomenclature that actually points at things, but it doesn't actually define how it works. An individual instance is not used to send data between two domains or CPUs. To send and receive the data, the user must create, register an endpoint in the instance. This allows for the connection of two domains of interest. It is possible to have zero or multiple endpoints for a single instance, possibly with different priorities, and to use each to exchange data. Endpoint prioritization and multi-instance ability highly depends on the backend used, and the endpoint is an entity the user must use. The endpoint is an entity the user must use to send and receive data between two domains connected by an instance. So basically what's happening here is there's a channel, and it can connect multiple participants, and these two participants can communicate via the channels. And it appears as though the participants in the channel, in this pipe that exists, some participants have a higher priority and some of them do not have as high of a priority. So there's prioritization. Sorry about that. There is prioritization in there, and we'll discover more about it as we go along. The endpoint is an entity the creation of an instance is left to the backend, usually at initialization time, and the registration of the endpoint is left to the user, usually at runtime. The API does not mandate a way for the backend to create instances, but it is strongly recommended to use the device tree to retrieve configuration parameters for instance. Currently, for an instance, okay, so I see. So even though the API does not say how to make these instances, the recommendation is to try and use device tree to shape the instances and use the instances, sort of allow that information to be in all the places that it needs to be. There's a few scenarios. Simple data exchange, send data between two CPUs, and endpoint must be registered onto an instance. See the following example. We make an endpoint bound callback, endpoint bounded, receive callback data received, and then we have an IPC ECT configuration, which gives us a name, and then it calls that the callback with bound and the received in there. And then in main we have like a device, and we have an IPC endpoint EP0, and we get the IPC node, and we open the instance on instance 0, and then we register endpoint on instance 0. We register endpoint 0 and endpoint 0 configuration. Okay, cool. And then wait for endpoint bound to be called. When it's called, that means something is happening. And then whenever that is called, and then later on we can make a message, and we can use the IPC service to send this message. Ideally, I think the way it's described, it means you're not going to end up interacting with this if you're working on the application layer, there's going to be already primitives, unless you're working on something really new. If you're working, excuse me, and let me know if I need to pose for questions. So if you're working on the application layer, it appears to me that there's going to be primitives that have been defined so that you can just go and use those primitives rather than actually having to define any new stuff. And then there's data exchange using the no-copy API. If the backend supports no-copy API, you can use it directly to write and read data from a shared memory location. So this is sort of like DMA stuff, where basically you have like a central buffer that is shared between the sender and the receiver, and what the sender basically writes into this buffer, and the receiver also reads from this buffer, and then you don't have a copy stuff and such. Yeah, so this is kind of the underlying layer that we're going to be using, but we won't see this in action because I think mailboxes are instances already. They're at top of this. So let's go and look at mailboxes because that's what we want to explore today. Perfect. And let me know if anyone has any questions. Let me check if the people on Discord are, yeah. Pardon me. Cool. If anyone has any questions, please do let me know. Let's now explore this mailboxes. So a mailbox is a kernel object that kernel objects is this. It's like a bunch of code. It's almost like I would say a message queue is also a kernel object, or mutex is a kernel object, or a semaphore. Basically, these are like little bundles of software that are in the kernel that you can use in specific ways. That's basically what is happening here. That's what we're being told here. So a mailbox is a kernel object that provides enhanced message queue capabilities that go beyond the capabilities of a message queue object. Okay, cool. A mailbox allows threads to send and receive messages of any size synchronously or asynchronously. So let's look at these concepts. Any number of hi Prabhu, you didn't miss that much. We're just getting started. If you have any questions, please feel free to ask. Prabhu says he thinks he missed a lot. So Prabhu, we're covering mailboxes today in Zephyr, and basically what we want to do is explore how to get to CPUs to communicate. And if you have any more questions, please do feel free to ask them. But I'm kind of going through the definition and we'll see what happens. So any number of mailboxes can be defined, limited only by available RAM. Each mailbox is referenced by its memory address. Okay, so you can make a sort of mailbox, sort of like a postal box. Yeah, hey Prabhu. Yeah, no problem. Prabhu says he missed previous streams. Yeah, we've had close to 115 streams, I think, right now. So there's a lot of content out there. You don't have to have seen all of it. Just, feel free to drop in for the ones that you're interested in, and feel free to miss the ones that you're not interested in. It's all cool. It doesn't really hurt. But yeah, and the topic we're covering today does not have any other prerequisite streams. We haven't covered mailboxes at all. Actually, today is my first day going to be my first day of using them, and we're gonna see how they work out. So don't worry too much. We're all learning together. We're all discovering this together. Hopefully, we find some meaty bugs and we see if we can do something about them, and we'll see. So you make a buffer in memory. You make a little area in memory. Let's I think, can I do Excalibur. So let's see if we can do something of this sort. So let's go here, and I think we can do yeah. So if you have a bunch of memory, so let's say you have so let's say you have a bunch of memory. You have a bunch. Let's draw it this way. So you have like, this is your memory, yeah? And then you want to go up here and say this is the memory. My voice is so feeble. Thank you, Prabhu, for letting me know. Is this better now? It could be that I'm far away from the mic, or that my thing decided to use something else. Yeah. I'm gonna bump up the audio. Thanks, Prabhu, for letting me know. Is this better? Please let me know if this audio is better now. Memory bank. I recently changed. Yeah, this is better. Thank you so much. I actually can just bump it up all the way to max, and then we'll see if it works. So I actually have a new microphone, whatever, because I'm trying to make these streams way better than they were. But do let me know if you notice something of a sort, or if I can improve anything. Thank you so much. So let's say you have a memory bank somewhere, and this memory bank is kind of like, oh, come on, how does that work? Yeah, let's just put it in. So you have a memory bank somewhere, and then let's draw a few lines, and let's put it red, and then we can say this is like RAM stuff, this is like RAM or ROM, and then we can go blue, and then we can say this is some come on, blue. And I want to draw a line. I want to draw a line. Let's say that, and then I want to go here and say this is a red one, and I'll label them, and then this is like, yeah. Let's say this is wrong. Okay. Blue first. So this is wrong. This is where you put all your code, and then let's say this is going to be red. Let's label this RAM. I wanna actually label it quite high so that we can use some more space in there, and then here you can say this is like let's label this down here flash, basically storage. You can like whatever you want to do, sort of like stuff. Hey Yasin, you didn't miss too much. I'm kind of just breaking down what we're going to. So a small recap, because you and Prapul just got in, and Prapul was complaining about the audio. Well, not complaining about the audio, well, recommending that the audio become fixed. So just a little recap. What we're going to do today is cover mailboxes. And I think this is, yeah, I won't start it again so that it keeps going. To be fair to Prapul now. We're going to cover mailboxes, and mailboxes are a way of doing an interprocessor communication service. Okay, so this is like a way of communicating data, doing communication between either two domains or two CPUs. And in my head, domain means something like APB, or like, you know, so we have like there's APB bus. And then there's also AHB bus, and there's two buses. There's this, yeah, so there's the bus architecture, and I think there's all of this domains or something. So there's and this is like in Axie we're going to cover later when we do data paths in FPGA, but not now at the moment. But what I'm talking about is like advanced peripheral bus and advanced high performance bus. And I'm assuming when they say domains, it's talking across these buses. And you can see, I think the STM32F4 block diagram. So let's look at this, just so that we can get some sort of example of domains and what do you call it? Domains and CPUs. So I want to do this one, and I want to get an image, and I want to get a block diagram, some block diagram that we can use, and let's visit this, and I can show you what I assume domains to be myself. Yeah. where are they? Yeah, cool. Yeah, so you see here, there's an AHP bus, advanced high-speed bus, and then there's an AHP1, and then as well as the AHP1, there's APB1 and AHB, APB2, and APB1, and these are like, this is a different, to me, this is a different domain to this one, and that's how you IPC allows us to do communication either between those, or when sometimes you have an SoC that comes with two. You have an SoC that comes with two, like the one that we're going to be using today. You have an SoC that comes with two microcontrollers or processors, and you want to send messages in between the two processors and see what happens. Cool. So any number of mailboxes can be defined, limited only by available RAM, and is referenced by a memory address. And this is what I was drawing. So what they're saying here is whenever you want to let's draw another one, and let's make it orange, and then I want to draw a little one here. Yeah, so let's draw a little one here, and in this one we can call it the mailbox orange. Mailbox orange. And orange. Cool. So what the documentation is telling us is that there's going to be some sort of give me a pen, and let's pick a pen here, and then I'm gonna make a big dot there, and then I'm going to Control A, and what do I group? I want to group all of this, group selection. Now I want to Control Z, and yeah, so I want to Control Z, and I want to Control Z, select everything here, and I want to move it here. Okay, cool. And let's do this. I want to delete that, so I want to move it here. Okay, so now let's think about this. What they say here, mailboxes. Any number of mailboxes can be defined, limited only by available RAM. Okay, cool. So you can fill as many mailboxes as you want into this space. And then what's the next thing? Let's put that there so that it's not there, it's not in the way. Can be limited only by available RAM. Each mailbox is referenced by its memory address, and that's why we put this dot here. So this dot here is going to be the address of that mailbox. So, and then this is going to be, if I do here, address of mail inbox, and this is going to be this is the thing. This is what we're going to be using to tell. This is what we're going to be using to talk to this mailbox, and then obviously it's going to have like a detail where it says how big the mailbox is, and then you know which kind of offset you're going to be using, and that's the big mailbox. Okay, cool. So now we have this box of mails. You can get messages into this box, yeah, and you can define as many boxes as your RAM allows you to, and then the mailbox has two more properties. So let's go back and draw it so that we can understand it. I like drawing, it makes me understand stuff really easily. So in here, okay, sorry, let's go here, and then we can draw another let's draw a little trapezoid, so that well, I don't know what that is. Is that a trapezoid or a rhombus or whatever? I don't know, I forget. Someone tell me. Bartholomew, tell me what that is. And then after that one, we can draw another one as well. And let's draw this one. And then we can label these ones. We can label this one. I'm going to label this RXQ. And then I'm going to label this TXQ. So we have messages that are coming into the mailbox and messages that are going out of the mailbox. And messages that are coming into the mailbox are put into the RXQ, and messages that are going out of the mailbox are put into the TXQ. And as we go along, I guess the documentation will tell us how this is. Thanks, Yasin. Yasin says this is a rhombus. As these messages come in and go out, you are put into the respective queues, and they can be, I think they can be, whenever there's a sender, they can put their message in TXQ. Well, well, we don't know. Let's go learn. Let's go learn. So, a send queue of messages that have been sent but not yet received. A receive queue of threads that are waiting to receive a message. Oh, wow. Okay, cool. So this is amazing. This is a list of threads that are waiting amazing. Yeah, let's put this here, and then this one here, list of messages that have been sent. Okay, so this is it's starting to make a lot of sense now, because now we can sort of visualize this thing and see the way it on. By the way, feel free to stop me and ask me questions. I'll try and pose as much as I can, but I'm trying to make sure this works out and see if we can actually explore this thing. So we have a list of threads that are waiting for messages and a list of messages that have been sent. We can follow like so yeah, a send queue of messages that have been sent but not yet received. So whenever they're received, the message is removed from the queue, it's popped from the queue, and then whenever a message is sent, it's pushed into the queue. And then a receive queue of threads that are waiting to receive a message, and I guess we're going to find some parameter that allows us to choose which message goes anywhere. A mailbox allows threads but not ISRs to exchange messages. Okay, cool. A thread that sends a message is known as a sending thread, while a thread that receives a message is known as a receiving thread. Each message may be received by only one thread. Okay, so there's no broadcasting. Okay, cool. So, okay, cool. So there has to be something that identifies where this message is going and where it's coming from, and who is waiting for what message, so that they can be matched. If they can be matched, then messages and threads can be CSPN. Okay, cool. And does the queue of threads get? We'll see just now. So a mailbox allows threads but not ISRs, which are interrupt service routines, to exchange messages. A thread sends a message. A thread sending a message is known as a sending thread, while a thread receiving is known as a receiving thread. Each message may only be received by one thread, and obviously it's only sent to sent by one. And as we just realized, broadcast or point to multipoint is not supported. Messages exchanged using a mailbox are handled anonymously, allowing both threads participating in a message to know and even specify the identity of the other thread. Aha! There we go. Now we know. So basically, whenever you're sending a message and whenever you're receiving a message, you get to specify who is going to be receiving it on the other side. And if you're receiving a message, you can specify who you are, and you can also I think you can also specify who you're waiting to send the message to you from. Do you have any questions right now? Because we've just covered how a mailbox looks like and the concepts here, and I think we have like sort of a mental model of how this works. Do you have any questions currently? Any questions? I should have brought water. I might have to actually walk out and get water and come back. Do you have any questions? No questions so far. Let me check the Discord. Maybe there's questions on Discord. No questions so far. Okay, cool. So let's now actually look at how to structure a message so that it actually gets sent and gets received. But I'm wondering, how do you identify a thread? So Zephyr threads have, if I recall correctly, Zephyr threads. Zephyr threads have a name, no? Yeah, let's look at thread creation. Threads must be created before it starts. And what do we do? I think you have to name a thread. Okay, yeah, there's. So Yasin is asking, I'm wondering, how do you identify a thread? And I'm realizing that I think if I recall correctly, whenever you're creating a thread, you have to name it. I think you have to name it. Yeah. There's this one. So there's that. You have to name. You do have to name your thread, and you have to give it kthread define. Kthread define. Let's look at kthread create. So kthread create, new thread, stack, area, entry, options. So what is it? New thread, uninitialized, pointer to the stack space. I think you have to name them, or you have to point to where they live. So that's kthread define. And Yasin says there's a 30-second delay between my my YouTube comments and me talking. Yeah, I think that's a physics barrier, isn't it? That's just the internet and how it works. I'm using a point-to-point connection on a farm, so I don't have exactly the fastest internet in the world. Yeah, there you go. So you name the stack, and this is, you can tell from this is one of those driver things, iterable instances. Yeah. Name of the thread. Yasin, does this make sense? You can identify a thread using the name of the saved thread. Does this make sense? Yasin? I think it does. I will wait for any questions from you, and we will see. So we know that you can name a thread, so you can identify a thread by its name. And because the thread's name has whatever name you give it and an instance number from the iterable sections. So Zephyr has something called iterable sections. Let me Zephyr iterable. And you can use this. This is not strictly Zephyr stuff. This is stuff that you can actually take into other programming languages and use them as you deem fit. It's not strictly just using Zephyr, so you can take it elsewhere and use it that way. But it's good to have a concept so that you can know what you need. So look at this here. So iterable section. Iterable section API used for defining iterable areas of equally sized data structures. So you make threads. If you make 5 of the same threads, they have the same size data structure, and basically you can give them the name, and then they can take a name and an instance number. And whenever you add an instance number, because you're making them as you're increasing the instances, you're also numbering them. So a combination of the name and the instance number makes the identity of the thread unique, if that makes any sense. So anyways, let's keep going with our stuff. Mailboxes. So like, how does a message, one of these things, so a list of messages, how does one of these look like? How does one of these messages look like? So let's actually choose another color so that we can actually start drawing messages. A list of messages. So like, how does one message look like? Let's draw it here. So first of all, let's give it an arrow, and then we can do this, and then let's actually draw a message so that we can visualize this. And then here we can say this is a message format. Okay, so let's actually go back. A message descriptor is a data structure. A message descriptor is a data structure that specifies where message data is located and how the message is to be handled by the mailbox. So am I passing in a function? Do I tell you this is the memory where the message is, and consume this message with this function or something. It appears that's what they need us to do, but let's see. And how the message is to be handled by the mailbox. Both the sending and the receiving thread supply a message descriptor when accessing a mailbox. It's like you send 5 messages, they're like call messages, and then you send 6 messages and they're like notify messages, and then when you're receiving, you can go like, give me a notify message from this sender, or give me a call message from this sender or something. I think so. That's kind of what I'm understanding here. Both the sending thread and the receiving thread supply a message descriptor when accessing a mailbox. The mailbox uses the message descriptors. There's code actually at the bottom, and we're going to look at this. It will come solid quite a bit soon. The mailbox uses messages descriptors to perform a message exchange between compatible sending and receiving threads. The mailbox also updates certain message descriptor fields during the exchange, allowing both threads to know what just occurred. Okay. So we have like labels or descriptor fields, and then these descriptor fields can be changed by both the sender and receiver, and also the mailbox itself. So the mailbox isn't just an area in memory. There's an entity of operable code that is a mailbox, and that it can do stuff. Basically, the mailbox can do stuff. A mailbox message contains 0 or more bytes of message data, and the size and format of the message data is application defined and can vary from one message to the next. Okay, cool. A message buffer is an area of memory provided by the thread that sends or receives the message data, and an array or structure variable can be used for this purpose. For this purpose. Okay, I see what they mean. So, and this, I think this is also kind of falls into the no copy stuff, because I go like, this area of memory, I'm gonna put in messages for you in this area of memory. The messages I put in this area of memory, you handle them like this, and the messages I put in that area of memory, you handle them like that. And because of all of these differences, the receiver also knows what to do exactly with the different messages. Okay, cool. So, and messages can be empty, so it could be like some sort of ping message that is notifies. Message lifecycle. The lifecycle of a message is straightforward. A message is created when it is given to the mailbox by the sending thread. The message is then owned by the mailbox until it is given to a receiving thread. The receiving thread may retrieve the message data when it receives the message from the mailbox, or it may perform data retrieval during a second subsequent mailbox operation. Only when data retrieval has occurred is the message deleted by the mailbox. Okay. So this actually makes a lot of sense. So I can notify you about something bigger than that. Let's actually look at this. So remember, we have this storage area. In my head, this is how it works. So we have a sender, we have a receiver, and then we have some fields. And basically what can happen here is that, and because we have let's actually draw two more. So let's draw a sender on this side. Let's do this. Let's draw a sender here, and let's do that, and let's draw a receiver here. So let's do this. This is a sender, and this is a receiver. Okay, and this is the thread. So this is some sort of thread that does stuff, and this one is also sun and stuff. So you see, we can take arrows and we can say this is that, and then this is that. Oh wait, and we can say this. I can take another arrow here, and we can point to here, and then we can say here. I think we can say location data in data in EEPROM X, and basically what can happen here is we can go like, yeah, like that. And then this, what I'm trying to show here, this data can be in some sort of storage somewhere here, and we can just take a pen and we can say this. So cool. So what can happen here is that the receiver, they can receive a message, they can go back, they can go into the mailbox and they can get this kind of message. But then this kind of message might tell the receiver, they might, this sender, they can go like here, you see this, and then let's put it here, fetch, fetch data from EEPROM X and do something. Okay, so this message itself exists in this queue. It exists in this queue up here, and then sender is in this list of threads, and receiver is probably in this list of threads. Sender doesn't have to be in there because sender might not be receiving. So what they're telling us is that while this is here, so this has a lot of these, so this has a lot of let's draw lines, and then let's draw them in blue, and then we can go like come on, just give me a few, more. Okay, cool. And then I want to draw an arrow, and I want to say this one is this. Okay, so that one is this, and then these are other ones. But what we're saying is this won't be deleted. This will not be deleted until this action is performed. And then once this action is performed, this message can be removed from the TXQ, and then you can go and it can be X'd out from the TXQ. So basically, you can have and remember, there is also the option of no copy. So if you do stuff no copy, you basically want something to, oh, I can copy paste elements. Yeah, I probably can. I guess let's try that. Yasin says I can copy paste, so let's try that. I want to remove that, and I want to copy this. Well, I want to do that, and that. And that. Oh no, it's shift then. Group. Can I group these ones? Group selection. Cool. And then I want to go, yeah, nice. And I want to copy. And I want to paste. And I want to paste. And I want to paste. Okay, cool. So what I want to do here, so that I can show what I'm trying to demonstrate here, is I want to squeeze this into the smallest I can. Can I make this really tiny? Yeah, something like that. See that? And then I want to make this one a little, also quite tiny. I'm having fun. I'm having a lot of fun. No, it's cool. It's cool. It's nice. We're learning together. Okay, cool. This is good. So Yasin is actually helping you. Feel free to tell me what things to do. So I'm doing this so that we can learn. This is all. There's no point to doing this. We only live once. This moment is only going to exist once. Don't worry about it. Tell me what to do. So okay. So this one is this one, and there's a lot of these ones like this. So what we were saying is until this instruction is done. So this is the message to the receiver. Until the receiver actually goes into here, let's now draw another line here. Let's draw a line here, and we can make this black, and then receiver fetch as from X. So this is just a hypothetical thing, and we want to say here until this is done, message message X cannot be deleted even though it's received. So, and then we want to label this. Let's come here and label this message X. Okay, cool. So what the documentation is saying is that the receiver can receive message X. So let's go here and say receive message X. But just because the receiver received message X does not mean and then this can I turn this around? Yep. So can I turn that around? And I can put it again. Send message X. So the receiver can receive this, but this is a secondary instruction. This is a secondary instruction until the receiver acknowledges to the mailbox. Yeah. Receiver fetches from here, then here we can take another orange one, and we can say here crap. Let's draw a line here, and we can say here receiver asks to mbox that X has been fetched. So until this is done, boom. Yeah, so let's do that. Let's visual stuff is cool. I need to get a whiteboard, and then I can do we do have a whiteboard. This is a whiteboard. So what the documentation is saying is the sender can send a message, the receiver can receive a message, but until sometimes there needs to be a secondary action that needs to happen, and then when that secondary action happens is then when the mailbox will delete this message. So that means that message will exist until this action is done. That's basically what the documentation is saying. That's all the drawing. That's what we're doing there. So, yeah. So I suspect Yasin has a very good question. Yasin asks, but how do you tell the mailbox about subsequent operations that can be done? Do you give it to some list of functions that are operations? I think so. So you recall this. There's this fields here. You see, there's this fields here. And we know of those fields because it's mentioned here. Descriptors. The mailbox uses descriptors to perform message exchange between compatible sending and receiving threads. The mailbox also updates certain message descriptor fields during the exchange, allowing both threads to know what has just occurred. Does that make sense? Yes, you're gonna get this 30 seconds later. But basically, how does the mailbox know, and how do the threads know? There's descriptors in the message, and they say what needs to be done, and then when something happens to this message, the mailbox tells the sender and the receiver. Make sense? Wow. This was supposed to be a thing where we were playing with this piece of hardware, but it's now become a deep dive into message mailboxes. Maybe there's a part 2. I don't know. I don't care. So let's keep going. Let us keep going. Does anyone have any questions before I drone on? I can drone on for hours. Does anyone have any questions about what we're doing, about what just happened? Any clarification you need? Any clarification needed? Let me put this up. And I can do this, and then I want to do fetching water will be right back. So I want to do that. Can I do that? This has been one of those really fun streams. It's ending up to be really fun stream, and it's really fun because I'm drawing and stuff. And this is all the fault of someone known as Nathan Kimutai. Nathan is the one who introduced me to Excalibur, and now I draw on my streams instead of doing code, but me and Yasin discover stuff. So give me a couple of minutes. Let me run out to the spout on the farm and get some water, and I'll be right back. And I'm back. Perfect. Okay, cool. So let's actually keep going with the stream now. Amazing. Thank you so much for waiting. So here we are. Let's do this. Cool. So we know what a message is. We know why the descriptors can affect how the messaging works and everything of the sort. So let's keep going now. The life cycle of a message is straightforward. A message is created when it is given to the mailbox by the sending thread. The message is then owned by the mailbox until it is given to a receiving thread. The receiving thread may retrieve the message data when it retrieves the message from the mailbox, or it may perform a data retrieval during a second and subsequent mailbox operation. Only when the data retrieval has occurred is a message deleted by the mailbox. Perfect. Okay, a sending thread can specify the address of the thread to which the message is sent. Or send it to any thread by specifying any. So basically what's happening here is how does a thread choose who to send to and who receive their message? Because what the question is now, because we know of those message descriptors, and the message descriptors help us in identifying where to send it, what to do, and all of those things. So you can either send to a specific thread, or you can do any, which means you have like multiple threads that can handle release. Imagine you have like a 16 core CPU, and 5 cores can or 6 cores can handle a type of message, and they all register for this, and then you go any and something also. A receiving thread to which it wishes to receive a message, or it can receive a message from a thread by specifying any. A message is exchanged only when the requirements of both the sending thread and the receiving thread are satisfied. Such threads are said to be compatible. So there's a compatibility arbitration that happens. Basically, threads, along with the message, they put up these conditions. Either this is the address, or this is the name of the thread that needs to receive, or something of the sort. And then this arbitration occurs. For example, if thread A sends a message to thread B, only thread B, it will be received by thread B if thread B tries to receive a message from thread A, or if thread B tries to receive a message from any thread. The exchange will not occur if thread B tries to receive a message from thread C. The message can never be received by thread C, even if it tries to receive a message from thread A or any thread, because thread A was sending it to B, and B can receive it either from A or N. And C can never receive this, even if it tries, because thread A was sending it to B. That's it. B is the only one with open options here. B can either receive from A or from anyone. That makes sense. So, message flow control. Mailbox messages can be can be exchanged asynchronously or synchronously. So this is like, you can receive out of order or send out of order, or you can also have a list where you just send in a certain way or receive in a certain way. In a synchronous exchange, the sending thread blocks until the message has been fully processed by the receiving thread. Okay, cool. In an asynchronous message exchange, the sending thread does not wait until the message has been received. It can send other messages before continuing. This allows the sending thread to do other work, such as data that will be used in the next message before the message is given to a receiving thread and fully processed. The technique is used for given message exchange is determined by the sending thread. Okay, so you can also, so basically this is I remember this. I remember some sort of same nomenclature from Elixir, from Erlang, where it went like Elixir processes. Elixir processes have some callbacks, and some of the callbacks can receive will block. Receive is blocking. Is the current is receive blocking. Something like that. So basically, there's a receive and there's a broadcast, and there's a send. Where is send? Process send. Require process and quote and so on. But basically, Elixir processes can send and receive messages, and actually, let's just go Elixir gen server. And like I was saying, like we just jumped. Sorry. So advice: handle call and handle cast. Handle call is basically a blocking one, a blocking receive, and handle cast is it will do it when it does it. Basically, if that's this is what I wanted to show. So in the same way, I feel like mailboxes can also have a cast or a call. And in a call, they have to actually say this: I'm waiting for you to give me a response if I call you. And then there's the other one of, I just cast the message, and whether you've gotten it or not, I'm gonna be doing something else, and if when you get it, let me know and we'll do something about it, but I'm going to be doing some other work, and I'll see you when I see you. And like they say here, the sender is the one who determines, because they decide whether they're using a blocking send or a non-blocking send, and such and so on and so forth. Okay, cool. So now we get to the meat of the stuff. We're now in a place where we can start looking at code and actually start defining this stuff. And basically, whenever you see this, that means the documentation is over, because we're going to be looking at code now, and it's gonna get real pretty quick now, which is cool. So there's always value in actually doing a little deep dive like that, because by the time you get to the code, it's the second time you're seeing things. You can actually you can reason about stuff rather than jumping straight to the code, and it becomes a problem. Any questions so far before we go on with this? For that, I was an hour to get to the code. That's good. That's amazing. Sometimes it takes more than an hour. All good from your scene. Okay, cool. No questions. So let's keep going. So implementation, defining a mailbox. A mailbox is defined using the variable of type KMBox. This is going to be some sort of struct that is defined in the kernel. You can always just open it up and look at it. That's pretty cool. I didn't know I could do that. Did I just open something new? Oh, and how do I close it? Did I just... How did I do that? And if I do that? Oh, what is this? No, I do not want unsplit tabs. Okay, cool. Wow. That's a feature of that's a feature of something. So KMBox, you can just I think you can open this. This is a struct that is in the kernel, and then we can initialize it with KMBox init, and KMBox init seems to take some sort of address of mailbox. So we define a struct KMBox, my mailbox, initialize it with my mailbox, and that's cool. Alternatively, we can use this. There's a macro that can do all of this for us. So you can pass in a name, KMBox define, and it basically you can just use this. You pass in the name, it will make the struct for you, and it will initialize the struct for you, and then you can now use it somewhere in the code. It's available for use in the code, and I think if I recall correctly, you'll have to do this outside a function so that it's sort of like global. Okay, and the following code has the same effect as the segment above, exactly what they said, and then message descriptors. So here we get to Yassine's favorite part of the world. So let's look at this message descriptors. So KMBox message, let's look at them. How does a KMBox message look? It has a data field, it has a size, it has info, it has TX data, so application defined information value, and then it has a sender's message data buffer. So this is, if you're sending some data in the message, it can be nil, I guess, but this is where that data is. And then it has a source thread, which is identifying who is sending it, and then it has a target thread, who is identifying who is sending it. And either can be I think either can be any. I'm not so sure, but we'll see. So cool. So that's a brief overview of that. So there's info, 32-bit value that is exchanged between the message sender and the receiver, whose meaning is defined by the application. So you can basically have a bit field, and you can use it to flag stuff. Remember, this message doesn't have to be the data you're sending. This is just to say, like, hey, we got a call, do something about it. Oh, hey, the GPIO went on, do something about it. You don't have to send the actual message here. It's just like, this is just a notification. And this is where no copy actually really works. Because if you want to send messages from here to there, and you want to do it in a no copy style, basically all I need to do is, to my receiver, I just need to send the address of the data that has come in. So if I have a sensor, say an image sensor, and it's consumed all this data from the real world, and it's put a lot of like big buffer somewhere, and I want some other thread or some other processor to know that there's some data somewhere, I can just tell them where the data is rather than actually copying the data and sending it to them. That's basically what happens, if that makes any sense. And then the size, the message size and data. So this is I will tell you where it is, I will tell you the starting address, and then I will tell you how big the message is, so that you know how many byte you're dealing with or whatever. TX data, this is pointing to the thread's message buffer. It can be set to nil, as I said, or null when sending an empty message. Basically, that means the information, the 32-bit value or flag you're sending is enough for the other person to know what is happening and whatever. And then this is the address of the desired thread. Set it to k-any to allow any thread to receive the message. Leave this field uninitialized when receiving a message. Okay. Aha, so this is how you identify yourself as a receiver or as a sender. So if you just leave it alone, you leave it to like the whatever default is there, I guess some sort of null. Then it means you are, if you don't have a target thread, you are a receiver thread. And if you don't have a sender thread, if you don't have a source thread, you are the source thread, basically. The mailbox updates this field with the actual receiver's address once their message is received. So even if you do send it to any, the mailbox still registers which any received it. So which core got this message. Later, when things start exploding in your system, you can actually use this as diagnostics. So which core keeps receiving this message, and then this core keeps receiving this message, and something keeps happening bad, and then you can go dig into the message and stuff. And then direct source thread, the addresses of the desired sending thread, set it to any to receive a message sent by any thread. Leave this field uninitialized when sending a thread, and then the mailbox updates this field with the actual sender's address when the when the message is put into the mailbox. So you can be like, source thread. If you leave it as blank, well, you can't. Okay, Yasin thinks they have a. Yasin thinks they have a weird, funky question, but it's actually quite a reasonable question. Yasin is asking, weird, funky question. What if a thread sends a message to itself? Well, you can't do that. You can't do that. You can't do that. But I think something in this remember we're talking about mailbox, and mailbox you would use it for interprocessor. So between domains or between domains or between CPUs. There is you can use a normal message queue. You can use a normal message queue to send yourself a message, and then you can have some way of handling it. And this is quite used. If I remember, there's say you want to handle something later, okay? So you can queue a message to yourself. You realize that you need to check some sort of flag later or something of the sort. So you can send a message to yourself so that you handle it at a later point in time. That's a valid way. But I think there's something that prevents us from. I don't know that you can initialize a message with both the target thread, and the RX source thread. I think the mailbox service will go like, no, you can't do this. I have a feeling that's a compile error. Anyways, maybe later we'll look at it. Maybe when we get to doing the code, we'll try and do it, and we'll see how we do it, and see what happens. But I would think it would be quite difficult. There has to be some rule somewhere, because this is now we're talking interprocessor. Like, this is between processor, between CPUs. So you don't want to do that. But if you wanted to do, I think what they are assuming is if you wanted to send a message to yourself, which is a valid way of using this thing, you can do that using simpler primitives, things like message queues and queues themselves, and so on and such. And maybe as we go along, we'll find some rule that enables us to know what this happens. Does anyone have any more weird, funky questions? weird funky questions before we look at sending a message, or any normal funky questions, or any just normal questions. They don't even have to be funky, just normal questions. Okay, perfect. No questions so far. So let's look at sending a message, and then we'll look at some code, and then we'll look at receiving a message, and we'll also look at some code, and I think we're done. And then we can go and run, I think there's an mbox, Zephyr has an mbox sample that we can run, and the moment we jump into the code for this thing, we're going to basically understand it, just because we've walked through all of this. There's two ways of doing it. You try and write the code, you get confused, you go to the docs, you read the docs, you know what you're doing, you go and read the code, it works. Both ways work. It's just a stylistic thing of doing stuff. Okay, cool. So let's actually look at, this is an IPC service, we're not looking at that, we can close that. So sending a message. What happens when sending a message? Sending a message. A thread sends a message by first creating its message data, if any. Next, the sending thread creates a message descriptor that characterizes the message to be sent, such as described in the previous section. Cool. And then finally, the sending thread calls a mailbox send API to initiate the message exchange. The message is immediately given to a compatible receiving thread if one is currently waiting. Otherwise, the message is added to the mailbox send queue. Okay, cool. Any number of messages may exist simultaneously in a send queue. The messages in the send queue are sorted according to the priority of the sending thread. Messages of equal priority are sorted so that the oldest message can be received first. And for an asynchronous send operation, the operation normally completes when the receiving thread has both received the message and retrieved the message data. If the message is not received before the waiting period is specified by the sending thread is reached, the message is removed from the message queue and the send operation fails. And when a send operation is completed successfully, the sending thread can examine the message descriptor to determine which thread received the message and how much data was exchanged, and the application defined info value. Yeah, basically, we have some sort of thing that gives you receive requests. So you can send a message and you can have like some sort of receive, it goes with some sort of receive request, and whenever a message is received later down the line, you're told who received it, what they did, and all of that stuff. And obviously you can use this for diagnostics, or you can use this for however way you feel like you need to do. A synchronous send operation may block the sending thread indefinitely, even when the thread specifies a maximum waiting period. The waiting period only limits how long the mailbox waits before the message is received by another thread. Once a message is received, there is no limit to the time the receiving thread may take to retrieve the message data and unblock the sending thread. So basically, if you do a synchronous call, it's a call that you have to wait for the receiver to receive and process and tell you something. You need the mailbox to tell you this thing has been received and it has been processed, and you can go forward. It's not just you basically, what they're saying is you have to be careful when you're doing this, because even if you give a timeout for when the message has to be received, you're still waiting. Even if the message does not be received, it appears you're still waiting. So you need to have some sort of way of falling out of that, or something. Like you can set an alarm in the future, and I've done this in a different context, but you can set some sort of alarm in the future, and whenever that alarm explodes, you can come out. And even when I did that, there was still a risk of me there was still a risk of me getting called and getting blocked, and I had to do some sort of stuff with my mutexes. I can give you an example of this. Zephyr Artos. So let's go here, and I think Zephyr, and we can go I think drivers I2C. I remember there's a good example here, I2C. No, this is drivers SPI, sorry. drivers SPI, yeah. And then in SPI, let's look at SPI NXP or something, SPI NXP for basically this little guy. SPI NXP SC18. It's gonna be somewhere here. SC18IS606C. Is the weight in here? No, it's not in here. So this is something I did. I remember that from here, and let's look at it. Let's look at the C. And I remember there was some sort of block here, mutex. I think there was a way we were doing, yeah, out here. So here you see. So basically, we were waiting for some RX, and then we would put some deadline in the future. Like you can see, we're putting a deadline 1 millisecond in the future, and then later along the line, we check if the thing has the deadline has expired, and if the deadline has expired, we fall out of this do while loop and such. So you'll have to do something of sort, basically, to if you do a synchronous message, you need to set some deadline later for you to recover from it. Otherwise, you can block yourself permanently, because if you get trapped in here, and it's not coming back, you're basically, the whole thing is trapped in there, and you're not going out. I think that's what they're explaining. Yeah, so let's keep going. Any questions so far? For an asynchronous send operation, the operation always completes immediately. This allows for the sending thread to continue processing regardless of whether the message is given to the receiving thread immediately or added to the sending queue. The sending thread may optionally specify a semaphore that the mailbox gives when the message is deleted from the mailbox. For example, when the mailbox has been received and its data is receiving, the use of a semaphore allows for the sending thread to easily implement a flow control. So basically, I can send an asynchronous message, and then I can use a gate to block myself from sending another one. If maybe I want to send an asynchronous thread message, but I want to know that it's been received or some timeout has passed, and then I can send another one. So I can use a gate to block myself from sending another one, and that way I implement some sort of pseudo flow control in such a manner. A thread that sends a message asynchronously has no way to determine which thread received the message and how much data was exchanged, or the application defined info supplied by the receiving thread. Okay, cool. So if you send it out, if you just cast a message, you don't know who will get it, you don't know if someone will get it, and you basically will not get a reply. So don't wait for a reply. You cast out a message, and you have some sort of way of knowing that it's handled by someone, and you'll find this out later. Cool. So let's actually look at some code. Sending an empty message. Let's look at this. Void producer thread. This is just the thread entry function I expect. And say we define a mailbox define. It's called a send message. And then while one generates some random value, prepare to send the empty message, and then message is size 0, tx data is null, and tx data target thread is any, and then send message and wait until a consumer received it, kmbox put and mbox, and then you have to wait. You're basically waiting forever, and if someone receives it, you go back into this loop, and this is just waiting until it's used. So this is sending I think this is a synchronous message because you're waiting. And I would think when it's asynchronous, you don't do any sort of wait. Sending message using a message buffer. Sending data using a message buffer. Okay, cool. So this is an empty message. You set message size is equals to 0, and tx data is null. So you're not sending anything. Okay, cool. So producer thread, you make a buffer of 100 characters, and then into buffer bytes used. You count how many is used. You make a mailbox as usual, and then you generate some data to send. Blah blah blah. You get it from somewhere. You get it from some serial input. You get it from some network. You get it from some sensor. Whatever. However way you get it, and then you copy the data from the buffer into this buffer into some source mem copy, buffer source, bytes used. So how many bytes have been used, you copy from the buffer, from the source into this buffer. Okay, cool. And then you basically you put some data in that buffer and you get it from somewhere. You get it from a sensor or something, you put it in that buffer, and then once you put it into that buffer, you make message info, bytes used. So info is what? Random value. Okay, cool. Bytes used. So you say I'm going to send you 6 bytes, and then you say I'm going to say the size is 6, and then this is the address of this is where you start, and then so you use an offset of whatever to get it, and then you set it to any, and then mailbox, and you wait. So this is also a synchronous send. You basically put my mailbox, send message, K forever, and you wait there and you see what happens. Info size and target layers fields have been updated basically from this person, and then you verify that the message was fully received. If send message size equals to that, prints a message drop during the transfer, printed. Yeah, cool. So you can on your end in your sender side, because this is a synchronous send, you can basically do that. And I think the only difference for async is this is k never, so you don't wait at all, or a k immediate or whatever. So you put it and you leave it by itself, if that makes any sense. Okay, cool. And then let's look at receiving a message. A thread receives a message by first creating a message descriptor that characterizes the message it wants to receive, and then it calls one of the mailbox API receive APIs. And the mailbox searches its send queue and takes a message from the first compatible thread it finds, and if no compatible thread exists, the receiving thread may choose to wait for one. If no compatible thread appears before the waiting period specified by the receiving thread is reached, the receive operation fails. Once the receive operation completes successfully, the receiving thread can examine the message receiver descriptor to determine which thread sent the message, how much data was exchanged, and the application defined info values applied by the. So you can send some sort of flag, you can send some sort of message, you can send some data in the message, and then the receiver knows what to do with all of these things. Okay. Receiving threads do not always receive messages in a fast in, fast out order due to the thread compatibility constraints specify the message descriptors. For example, if thread A waits to receive a message only from thread X, and then thread B waits to receive a message only from thread Y, an incoming message from thread Y to any thread will be given to thread B, and thread A will continue to wait. So it's not deterministic when you'll get the message, basically. So just because you started waiting before another person doesn't mean you get your message before the other person. That's cool. The receiving thread controls both the quantity of data it retrieves from an incoming message where the data ends up. The thread may choose to take all of the data in the message, to take only an initial part of the data, or to take no data at all. Similarly, the thread may choose to have the data copied into a message buffer of its choice. And the following sections outline various approaches to receiving the receiving thread message. Okay, so receiving data at receive time. The most straightforward way for a thread to retrieve message data is to specify message data when you're registering into the KM box. You can be like, this is. Whenever you get a message, put it in here, and then basically there you go. So you make a KM box receive, buffer of 100 characters, I total, and then prepared to receive. You say I want 100. Info doesn't have to be 100. Info can be anything. It just has to be 32-bit. The size, you tell it what you want to receive, and you tell it you want to receive from any. And then once you get a message get an item, you can wait as long as needed. So this one is waiting forever. This can be loaded into that, and then verify that the message was fully received, and then compute whatever you want to do and do something else, and then this thing does itself again. So you go, basically you're re-registered into the mailbox again for free, whatever. Retrieving data later using a message buffer. A retrieving thread may choose to defer message data retrieval at the time the message received, so that it can retrieve it later or do something down the line with it, because you might get some sort of signal, and then based on that signal you decide you want to do something, or want someone else to handle it, or you want to wait for something else, or you want to wait fetch something and then do something with it, and then you can do something of a sort. So if the message descriptor is size 0, then either the sender's message contained no data, or a receiving thread did not want to receive any data, and the receiving thread does not need to take any further action since the message has already completed. If the receiving message descriptor is non-zero and the receiving thread still wants to retrieve the data, the message must call kmbox_data_get and supply the message buffer large enough to hold the data. If it is a non-zero and receiving thread does not want to receive the data, the thread must call and specify a message buffer of null, and the mailbox delete the message. Okay, cool. So you might get a message, and the info, you realize like, oh, this is too late. I don't care about this right now. So you can still receive the message and tell the mailbox, delete it. I don't care about it. I don't have to use it. Okay, delete it. I don't care about it. So that way you can sort of like, sample yourself and do stuff yourself. And then the following code uses a mailbox deferred data retrieval mechanism to get message from a producing thread only if the message meets certain criteria. So yeah, basically, like I said, you might receive data, you might determine that it's too old and you don't care about it. So you go like, nah, this data was from 5 minutes ago. 5 minutes is too old to do the thing I need to do. The set light has already passed, so it's gone now. It's useless. It's gone away. Just delete it. So let's look. You register as usual. You say what you're going to do, and then you say you put a null here. So you got null here. Okay. This is a null. This is the buffer. You see, previously this was a buffer. Yeah. So if you put a null here, this means you're not going to receive it now. And then is message type okay? Receive message, and then now you can receive the message here. You see? Now you can retrieve the later if you've received the message. If you didn't, else you can do something else. You can data it and you can do it and whatever. The code section was a bit fast fetch, but it gets faster like that because we spent quite a bit of time actually setting up to this so that it can work out. So let's go and try and I believe in the Zephyr API there's a sample demonstrating how to use the Mbox API. Let's see, Mbox data. We can even try this as well. So let's try both of them and see what happens. I have an NRF54L. So I have this one, NRF54L from Zephyr. Well, not from Zephyr, from NRF. I have this kit, and this is a kit here, and it's got quite a lovely arrangement of GPIOs, which is quite weird for me. I'm used to them being on the side, and then there's a port P2, port P1, and port P0. We're not going to be using those. What we really want to do is play around and see if we can communicate between the CPU app and the. So first of all, let's look at this. So this it has an ARM. You see here, ARM architecture. It has an ARM CPU. Yes, look here. So it has a CPU app, and then additionally to the CPU app, here's a Flipper application here. And the Flipper application is a VPR implementation of Nordic Flipper, Nordic NRF54L15. So let's now go run this on hardware. So let's look at this. So this, if I go into the documentation somewhere, yeah. So you have an Cortex M33 here, and then you also have a RISC-V coprocessor here. And what we want to do is use a mailbox and send messages between these two processors. That's basically what we're going to try to do. And we happen to be in luck because Zephyr has a sample for this that we can use. So look at this. We have that, and we have that, and basically we can use that to write the stuff. So let's look at this. Oh, we need to use this build, so let's actually build that. Let's build that and see if it works out. So clearly I've been trying stuff, but let's actually do that. Let's build a CPU app, samples Blinky, but I don't want to sample Blinky. I want samples drivers Mbox. Okay, and then along with that, I want to do a sys build, to actually run it in sys build. You can put that flag anywhere, I know, but I'm gonna just put it where they put it, so that sys build. Sys build. I wonder I have to use sys build, but it's fine. So this should be nice. Okay. Let's put it in. Let us flash it, and then we'll go and look at the code as well, obviously. Cool. And then I'm gonna go west flash. That should go in, and then before we do the next thing, we want to also write the flipper app, and this here it is. So west build, we're gonna build for the flipper application, and we're gonna build it fresh, and then we're gonna send it in, and then we're gonna look at the code for this, and that's gonna be nice. That's going to be nice. The code will look very similar because we already understand what it looks like. We already understand what is happening here. We just want to see some sort of ping pong messages between the both of them. And there you go. It's building. That's amazing. Oh, that was MCU boot. And I'm going to do a west flash. Cool. So that's in. So this here I have, oh, snap. Control A, Control X. I'm gonna do that to reset that one, and then I'm gonna go here, Control A, Control X, and then I'm gonna do that. So SCM0 belongs to the flipper, and SCM1 belongs to the CPU app. So there you go. So that's built. That's booting. And that's on, and she's waiting, but we have no response. This is not a good thing. Want to reboot again? See? And coincidentally, we only, okay, so what is happening here? So this one is sending, it's pinging. This should be ponging as well. Let's look at this Mbox one. Do I really have to do that instead of do I really have to do a debug, not a flash? Because I see here they go like, you build this and then you do a debug. Maybe. I did a flash. I did not do a debug, so let's see. Okay, west debug. That does not seem to help. Continue. Next. Well, load. Break main. Continue. Next. See? So I do not want to do that. Quit. I would rather do a flush. Why isn't the flush working? Please don't tell me we've found something. Reboot. Oh no. Oh no. Oh no. We found a bug. We found a bug. So let's try mbox data first of all. Let's try mbox data, and then we can look at, and then maybe we can find out whether we want that. We want to look at that. Yeah, let's look at mbox data first of all, just so we understand whether this is. I hope it runs. Okay, so this is -- pristine. Let's debug. I always forget. Running code from GDB. Well, no worries. Yasin is leaving. Yeah, I'll do them more. I'll do a lot of them. I see. I'm gonna hang out a bit and do some more discovery here before I stop, and then we'll see. It seems I don't know how to use West debug. That's actually what it seems like. So West debug. we do have a fatal error. We do have a fatal error. So that's continuing. Okay, this gives us a chance. This gives us a chance. So let's actually look at Zephyr under to line. Thank you so much. That was cool. Yeah. So yeah, that's gonna crash, and then we're gonna get that, and then what do I need to do? I don't want to do that. It's already done, so I just don't care about that. Yeah, on this. I actually have some notes on how to do this with GDB. Yeah. No, I don't want to dump assembly. Yeah, cool. LR on the link register. Which one is LR? Yeah, that one. Okay. Let me see. RM none ABI address line. So let's actually just copy that one. Do I have that? I should have that. Ooh. Okay, I'm gonna end the stream and we're gonna go hunt this. Actually, before we do that, let's actually just hunt it now, and then once we do find it, we can stop the stream. Once we do find the offending register. So ls build let's build Zephyr, isn't it? Let's build. Is it? Let's build Zephyr. Can I do? Let's build mbox. Yeah, mbox Zephyr, and then we have a Zephyr.alpha. So cool. So yeah, okay, cool, fine. Let's go find out what this link register is going to be. So what I want to do is go back here, and I want to point that into map to source with. So that Zephyr elf. Okay, let's do that. Clear. I want address line build mbox Zephyr Zephyr elf. Yeah, but I want to specify that as the elf, and then what I want to do is get this person. So where is that? Zephyr project main 37, mbox main 37. So we know where that issue is. So and vim. So let's go and look at that issue. Source main 37. Okay, cool. pf mbox source c main. Okay, cool. 37j could not enable RX channel. So why is that? So we're already in here. Why can I not print K? Why can I not print K? But I never get on any of these prints, so that's the problem. What is the problem? So I can actually just, yeah, that's fine. That's fine for now. So what is it that, what do we get? So LR XPCR R14 R15 here. This is the faulting instruction, so let's find that. Let's find you. Oh no, something in the VPR. .h. VPR.h. VPR. What is it? VPR. NRF54H. NRF. VPR. H. Modules. Do I need to do a West update? Where is this? Modules HAL Nordic. Do I need to do a West update? Do I need to do a West update before I do anything here? Quit. Yeah. Can I? Yeah. Do I need to do West update or something also? Modules HAL NRF. HAL Nordic. Let's see. Because why is that failing? Yeah, let's try that. Just wanting to discover where this error is coming from, and then we'll stop today from there, because I'm probably just missing some sort of little update, and then this should be running. Because we should be getting pings and pongs on the other side, but we're only getting pings, so that's not cool. Okay. And then I want to do a West flash. West missing one, and let's see what happens. Not cool, not cool, not cool at all. Same place. Precise data bus error. Copy. So what does that mean? I bet you I'm missing something small, like a K config or something. Yeah, I'm not using a bad pointer unless this pointer is bad. Mbox src main. Unless you're telling me this, but why isn't it? But why doesn't it even print that? It just fails so quickly because it fails here. It actually fails here. I mean, let's go look at the boards here and see NRF 54L15 and yeah, this one. I want to see this one. Mbox consumer VX. Okay, status okay, TX is okay, TX is fine. I'm gonna ask in the Nordic group. I'm not gonna bother finding out, and then maybe there's something I'm missing. So I'm gonna take this to the Zephyr Nordic group, and then we'll figure it out from there. I could be missing something. Let's look at the Mbox documentation again. Ronnie's debug. There's nothing that prevents us. Let's see, browse. There's nothing that prevents us from running this. I wonder if this is because we're on a newer Zephyr. I wonder if this is because we're on a newer Zephyr. I wonder if this is. Anyways, let's stop there today. It's been 2 hours. That's been amazing. As always, my name is Zach, and it's always amazing to discover with everyone. And cheers. And remember to be daring. Remember to find out, and remember to try. Thank you so much.